All right, here's a review of 1.5. I'm not going to review the whole thing because I want to teach Coulomb's law through direct instruction. But here we are going to focus on this part. We are going to review electron configurations, the shells, the subshells, and then leave the rest of it for when we are together in September. So again, skipping Coulomb's law. I love Coulomb's law. You'll find it's my favorite law. All right, electron configuration. So what electron configuration does is shows you the levels, the shells, the subshells that the electrons are in the atom. It's that information that will then impact things like how big the atom is, what ion it's likely to form, how much energy it takes to form different ions, so all sorts of things. So this is kind of where we start. So again, background, what the electron configuration is, 1s2, 2s2, 2p6, 3s1 is an example. So again, we've got the arrangement of the electrons in the atom, so you have levels. So the levels indicate the distance from the nucleus or the shell. You can think about sometimes we have, so if we have all of our protons in the nucleus here, the Bohr model is one that we commonly use. It's not correct, but it works really well. So right there, what just got erased from my circle. So this would be shell number 1. So this would be the first energy level. And according to this configuration, there are 2 electrons in that first energy level. They're in the S sublevel. So that talks about the shape. You don't need to worry about what the different shapes are. So don't get hung up on that. But the S and the P, when you see these letters, S, P, D, F, they're telling you the subshell. And then we've got the orbital. The orbital is the region where the electron is likely to be found 90% of the time. Again, we don't get too in-depth into that. We just need to know how to use it. So for this configuration, we've got 2 electrons in that first energy level. Then one of the key things to recognize is this second energy level is going to be further away than the first. That's the thing that's going to come in a lot. It's further away. Because it's further away, it can be larger, and you can fit more electrons in it. We would have 8 electrons in this one. And we don't often draw these Bohr models, but you'll see them as we start talking about periodic trends in Unit 1. And then, of course, we have a third energy level there. And so I would draw a third one to kind of represent, to keep my model going. It's a terrible circle. It doesn't even recognize that that is a circle. So let's put you here. There we go. And according to the electron configuration, there is 1 electron in that third level. The third level, this outermost level, this is also known as the valence level. That's going to come in quite a bit because those are the electrons that are most likely to leave. Hopefully you recognize that, well, that makes sense because that electron is furthest from the nucleus. Again, one of the half of chemistry is that opposite charges attract. So the further an electron is from that positive charge, the less strong the attraction is. All right, so what you need to be able to do is identify what element we have based on the electron configuration, and also write an electron configuration. So here are a couple things you can do. You might be thinking, wait a minute, on our periodic table one time, you had us label a bunch of stuff. And so I know where the third level is, I know where the S block is, and 1 electron in. So this one happens to be, 3s1 is sodium. This is the configuration for sodium. So I want you to take a minute, look at your periodic table, see if you can kind of put those things back together yourself, but I will also review them. So quick review, the different shapes of the orbitals. Like I said, you don't need to worry about committing this information to memory, but the S has 1 orbital in it. It can hold 2 electrons. The P subshell has 3 orbitals. Each can hold 2 electrons. The Ds have 5 orbitals. Each can hold 2 electrons. So the total number of electrons in each of the shells, you can have 2 in the S, 6 in the Ps, 10 in the Ds, and then 14 in the S's, which of course correspond to the shape of the periodic table. Yep, so here are the rules. Pauli exclusion principle, no 2 electrons in an atom can have the same set of 4 quantum numbers. What that means is no two electrons are identical to each other. Aufbau principle, they start filling in the lowest energy levels first before filling in the higher energy orbitals. So when you look at the order, we've got the 1s, the 2s fills in, the 2p, the 3s, the 3p. Then you'll notice the 3d is over here. The next one that fills in is the 4s. All right, so that is by looking at your periodic table. If you just did that method where we just start marching across the periodic table and write things in order, that order comes out of that. The last one is Hund's rule, that the most stable arrangement of electrons has the maximum number of unpaired electrons. So this doesn't come into play too much for what we are doing, but just makes that the electrons, since they're both the same charge, the closer they are to each other, the less, like, there's more repulsion between them, and so that makes it less stable. Here is, I don't know if some of you have seen this image, some of you have not, but this is the order that they fill in. So this is, you've got electrons, 2 of them can fit in the 1s first, and then the 1s is full, and then the next 2 electrons go into the 2s, and then the 2, oops, I screwed that up, the 2p. And again, this is orbital notation, which we don't really use in AP, but some students find it really helpful to use this one first. The 3 electrons go into the 2p, and then they double up, and you just keep going up the chart in energy, because again, the lowest energy, the 1s is the one with the lowest energy, and it goes up from there. All right, this is probably what you remember. We had you label your periodic table, the periods, which are the energy levels for the main level, for the S and the P's are there. And then we have the S block was this chunk, and a lot of times helium, we kind of moved it over there. We have, notice the P block, and then we have the D block in the middle, and remember that the D block is 1 down from the S block. They don't have the same number. And then we have the F block, which we really don't use the F block very much, but this is the 4 and the 5. So you might want, if you want to write this on a periodic table, you need to be able to look at a periodic table and just be able to write the electron configuration, but hopefully it comes back to you pretty quickly. Okay, so just do a little bit of practice. Write the electron configuration for sodium, bromine, and zinc. So let's take a look at this and start with sodium, although sodium was one we already did, but hey, that's okay. Let's just review how this works. So sodium is here, so that's where I'm going to end. So I always start with the up at the top left corner. I always start with 1s, and I can fit 2 electrons in the 1s. So I take care of that one, and again, helium kind of lives over here. Then I have to go to the next row, and I'm in the second row in the S block. And again, there are 2 electrons, and then that fills that up. Then I keep marching across the periodic table, and then I'm into the still second level. Now I'm in the P block, and now there are 6. 1, 2, 3, 4, 5, 6. So that fills up, and then finally sodium is here, so I have to write that last electron. 3s1 is my configuration for sodium. All right, so for bromine, bromine is right down here. So I'm going to let you, if you want to, of course, you can always pause the video, or if you're like, wait, I remember this, I can just go ahead and do that. But I'm going to start marching across. Again, I always start with the 1s, 2, and then the next thing is the 2s2, 2p6, then I have the 3s, 2 electrons in there. All right, so I've gone here, here, there, there. Now I go across. The 3s is the next one, and I have enough electrons to completely fill it up, so 3p6. I might have said 3s, I meant 3p. Then I go to the 4th row, so I have 4s, 2 electrons there. Then I go across this, the transition metals. So now it's 3D. You notice it's not 4D, it's 3D, and there are 10 of them. And then I stop at bromine, which is 5 electrons in, so 4p5 is going to be my final part of my configuration. All right, then for the last one, zinc. It's kind of, if you look at this pattern, you might just be able to realize, hey, zinc ended there. Zinc is right there. That ends at 3d10. So again, the configurations always start the same. And it ends at 3d10. Okay? All right, noble gas notation. So this is the one we often use, we're more likely to use when we ask you to write out a configuration, because the reason we do this is because we want to be able to focus on the valence electrons, not the core electrons. All right, the core electrons are, if I go back to my model, there's my model. The core electrons are everything inside here. All right, so those are my core electrons. Those don't really participate in bonding, except there are some situations where they do, and we'll deal with that. Actually, we don't deal with that at all in this class, but they can. But what we're focused on, what's going to participate in bonding, are the valence electrons. And so that's why we write the noble gas configuration, so we can just focus in on those valence electrons. So the noble gases, of course, are the last group, group 18. We call them noble gases because they tend not to bond. Some of them, they can bond, especially if they have electrons in the d orbitals, but they are the most stable configurations, and so we kind of use them as a reference for all the other configurations. So for the noble gas configuration, what we're going to do is we are going to put the noble gas symbol in brackets and then put the valence electrons after the brackets. So let's start with cadmium, Cd. So cadmium is right here. The noble gas configuration that would make sense to start with is krypton. So I go up a row and then find that configuration. So I have krypton, Kr. Then beyond krypton, I just care about the valence electrons, 5s2, and then 4d10. All right, for carbon is, sorry, I want to correct something I said. When we talk about valence electrons, these actually technically are not valence electrons, the 4d. The only valence electrons we have are the 5s. So, but again, it allows us, we're going to be able to see all the valence electrons, but there might be some, the d's are never going to be considered valence electrons. The valence electrons are only in the s and the p orbitals, because you can see in the d, they're in the fourth level. So again, the model I was drawing earlier kind of falls apart sometimes. It's good for some things, but not good for everything. But key thing to remember when we talk about valence electrons, we're talking about electrons in the outermost energy level, which in this case is the fifth level, and they will only ever be electrons in the s and the p. All right, so let's go back to carbon after that quick review. And again, if anything is like, wait, I don't understand something, listen to it again, look at other resources, ask questions. So yeah. All right, carbon is right here. So carbon, we've got the noble gas that makes sense to start with is helium. It's actually the only one. And then 2s2, 2p2. All right, and then Pb, which is lead, is going to be here. Ooh, I did something fun here. I'm going to send us into the F block. Okay, so we're going to start with xenon. So I'm just going to stay up here in the table to write this one for Pb. So I start with xenon. All right, and then I'm going to go through the 6s. So we have 6s2. Then something that we really didn't deal with in first year chem, because it just didn't make sense. We now, from barium, we actually don't go across to lanthanum, La, you actually have to go down into the F block. All right, so you can see if you look at the periodic table numbers on your actual table, barium is element number 56, but element number 57, actually lanthanum is right here. This table is a little misleading. Lanthanum and AC are actually there. So, wait a minute, what is going on? Hold on. What? They made a mistake. Oh, this is fantastic. I just noticed this, whoever did this table kind of made a mistake here, and these are actually in the 5D, but it doesn't matter. We rarely ask you to go there anyway. So we have xenon 6s2, 4f14, 5d10, 6p2. Okay? But remember, if we asked you for the valence electrons, you're not listing all of them. The valence electrons are solely, if I said write the configuration of the valence electrons, it would just be 6s2, 6p2. All right, I would ignore everything else, and my valence electrons are just, there's 4 valence electrons, 6s2, 6p2. Okay? All right, and that's electron configurations. So again, you can work on those problems. Like I said, the Coulomb's law, I want to work on that in class in September.